Hello students, welcome to the next class. In this section, we are dealing with the Banach spaces. So in order to introduce these Banach spaces, I would like to define what is the definition of a sequence convergence of sequences in normed linear spaces. So for that we will have a definition. So the definition says that suppose we have a normed space X. X is a linear space together with a norm. Okay, then it is a normed linear space. Then if consider a sequence Fn. Fn means F1, F2, F3, etc. It is a sequence. We say that this sequence converges to some F, which is an element in X, which means that you find out the norm of Fn minus Fn. That means the difference between Fn's and this F. Clearly Fn minus F will be an element of capital X because it is a linear space, right? Since it is a linear space, it must be closed under vector addition, and every element it has an inverse, right? So minus Fn will be the inverse of Fn's. Then F minus Fn will be the vector addition between two elements. So that will be clearly contained in capital X, right? So you find out, we can define what will be the norm of F minus Fn. Then you find out its limit. When that limit goes to 0, we say that Fn is a sequence which converges to F. Okay. In this case, we say that we write sequence Fn converges to F in X. Or I can write limit n tends to infinity Fn is nothing but F. Okay. So this is the definition of convergence of sequence in normed linear spaces. Now, what will be the definition of Cauchy sequence in normed linear spaces? If the sequence Fn is said to be Cauchy in the normed linear space X in X, if for every epsilon greater than 0, there is a natural number n such that norm of Fn minus Fm is less than epsilon for every n and m greater than or equal to that fixed integer n. Okay. Now we have one more definition. A normed linear space is said to be complete. Normed linear space is said to be complete if every Cauchy sequence converges in it. If every Cauchy sequence in X converges to an element in capital X. Okay. Then if a normed linear space is complete, that space is called Banach spaces. So what is a Banach space? A complete normed linear space is called a Banach space. A complete normed linear space is called Banach space. Banach space. Complete normed linear space is called a Banach. For example, I consider a real line with modulus, usual modulus. Okay, I can prove that this is a normed linear space. Okay, which is a normed linear space because modulus satisfies all the conditions of norm, which is a normed linear space. You know, real line vector space and usual modulus will be satisfies all the axioms of normed linear spaces. Therefore, it is a normed linear space. And I can prove that the real line is a complete space. Because if you consider a Cauchy sequence in R, suppose let Xn be a Cauchy sequence in R, then you know every Cauchy sequence in R will be a convergent sequence, right? It is a convergent sequence. And we know that real line is then actually Xn is a convergent sequence. So since it is a convergent, Xn must be converges to some X in R, right? So every Cauchy sequence will converges, and that converging element is also belongs to real line itself because it is closed. Therefore, real line is a complete space. Real line R is a complete normed linear space complete non-linear space. Therefore, it is a Banach space. Therefore, it is a Banach space too. So, in general, I can say that every Rn is a Banach space. R, R2, R3, etc. N copies of R will be a Banach space. Okay. One more example. You consider C of AB. What is C of AB? C of AB is collection of or set of real valued continuous functions defined on closed interval AB. You can prove that this is a normed space. Under the norm, we are defining for f belongs to C of AB. I define norm f is equal to maximum of modulus of fx where x varying over closed interval AB. Okay, that means maximum of that function, and this norm is called a max norm. And I can prove that this max norm satisfies all the conditions of norm. Therefore, C of AB is a normed linear space. Okay. Now we are going to prove that the C of AB is a Banach space. For that, we need to prove it is a complete normed linear space. So we prove C of AB is complete. So for that, we want to prove that every Cauchy sequence converges in it. That means suppose we have suppose every Cauchy sequence, suppose it converges to some element, that element is also belongs to the same space. Okay. So how will you prove this? I take let Fn be a Cauchy sequence in C of AB. Okay. Then by the definition of Cauchy sequence, for every epsilon greater than 0, there is a natural number n such that for every n and m greater than or equal to integer n, I can say that norm of Fn minus Fm is less than epsilon, right? Here norm is max norm because elements are belongs to C of AB. Norm on C of AB is maximum norm. So I write max norm less than epsilon. So what is maximum norm says that, which means maximum of modulus of fx. Here modulus of fnx minus fmx, right? Fnx minus fmx such that x varying over closed interval AB is less than epsilon. So maximum of modulus is less than epsilon means that modulus value will be less than epsilon, right? So modulus of fnx minus fmx is less than epsilon for every n and m greater than or equal to some fixed integer n and for every x in AB. Right? So corresponding to every point small x, if you fix some x, then fnx minus fmx is less than epsilon for an n and m greater than or equal to n, right? So which implies fnx, okay, point wise ആണ് ഞാൻ പറയുന്നത്, fn of x, okay, you consider the sequence fn of x, which will be a sequence which is Cauchy, right? Which implies fnx is a Cauchy sequence, in where since x belongs to AB, fn of x is an element belongs to real number because these functions are real valued functions. So fnx minus fmx will be a real valued function, right? So fnx and fmx are real numbers. So fnx is a Cauchy sequence in real line in R. And we already said real line is a complete space or it is a Banach space, right? Since R is a Banach space, by the property it will be complete. So every Cauchy sequence will converges in it. Therefore this Cauchy sequence fnx will converges in R. Since R is Banach, the Cauchy sequence fnx converges to a function f in R. Converges to a function f of x in R. Fnx will converges to fx in R. Fny will be converges to some fy. Okay, corresponding to this variable x that will be varying. Okay, now you consider this number fx. For every x in closed interval AB, I can have some element fx in R. So this fx can be considered as a function, right? Then f is a mapping from closed interval AB to R defined by what is f of x? For every element x in closed interval AB, f of x is limit n tends to infinity corresponding fnx, right? fnx എന്ന് പറയുന്ന സീക്വൻസ് കൺവേർജ് ചെയ്യുന്ന ആളാണ് എഫ് ഓഫ് എക്സ്. അതുകൊണ്ട് ഓരോ എക്സിന് അത് വ്യത്യസ്തമായിരിക്കും. അതുകൊണ്ട് എഫ് എൻ എക്സുകളുടെ ലിമിറ്റായിട്ട് ഞാൻ എഫ് ഓഫ് എക്സിനെ ഡിഫൈൻ ചെയ്താൽ ദാറ്റ് എഫ് വിൽ ബി എ റിയൽ വാല്യൂഡ് ഫംഗ്ഷൻ. Okay, now I am going to prove that our sequence fn converges to this function f. Now I claim that sequence fn converges to f uniformly, not in the pointwise way, uniformly on E, almost everywhere. Okay, only real valued function. Okay, on closed interval AB, I'm sorry, on closed interval AB, fn converges to f uniformly on closed interval AB. Now how will you prove this? Fn converges to f means we have the definition: a sequence is converges to a function f if limit n tends to infinity, norm of fn minus f is 0. Okay, so I consider what will be norm of fn minus f. What will be norm of fn minus f? That is equal to actually maximum of here we have to consider the maximum norm. So maximum norm of fn minus f is equal to maximum of what I can write, modulus of fn minus f of x such that x varying over AB, which is equal to maximum of modulus of fnx minus fx such that x varying over AB. Okay, that is what will be maximum of fnx minus fx. Since at every point x the sequence fn of x is converges to f of x, therefore their distance will be modulus of fnx minus fx will be 0, right? Because fnx converges to fx, actually, which implies modulus of fnx minus f of x will be 0. Because the norm on real line fnx and f of x are real numbers, then their difference is 0 means their norm on R is nothing but its modulus. So here I can write norm of fnx minus f of x equal to 0 on R, but norm on R is modulus. So instead of norm I can write modulus of fnx minus fx equal to 0. Okay, so this will be goes to 0, so maximum will goes to 0, so we get 0. Therefore limit n tends to infinity, norm of fn minus f, maximum norm of fn minus f equal to 0, which implies fn converges to f. Sequence fn converges to f uniformly on closed interval AB. Now we need only prove that this f belongs to our C of AB. So we take a sequence fn which is Cauchy's sequence. Using that Cauchy's criteria, we proved fn of x is a Cauchy sequence in real line. Since real line is a Banach space, that fn of x will converges to some f of x. We take that f of x as a function and we proved that our sequence fn is uniformly converges to f on AB. Now we are going to prove that that converging element f is also belongs to C of AB. We have f of x is equal to limit n tends to infinity fn of x for every x in AB, right? Okay, so we have sequence fn converges to f. Okay, and what is this fn? Each fn is continuous, because each fn's are belongs to C of AB. C of AB consists of continuous real valued functions. So each fn is a continuous real valued function, and the convergence is uniform, we have uniform limit theorem. Okay, uniform limit theorem says that if the sequence of functions which are continuous and converges to some function f. When the convergence is uniform, that converging function, that element will be also continuous, right? So by uniform convergence theorem, convergence is uniform, comma, by uniform convergence theorem I can say that this will be fn, f is real valued continuous function. When f is real valued continuous function on AB, this function will belongs to C of AB. So every Cauchy sequence in C of AB converges to a function in C of AB. Therefore C of AB is complete, and it is a normed linear space also. Therefore C of AB is Banach. C of AB is Banach. When E is a measurable set, we can prove that L infinity of E is also Banach space. What is L infinity of E? L infinity of E is equal to collection of essentially bounded functions. Essentially bounded functions on measurable set E, subset of R. Okay. So we know what is the norm on L infinity, right? Norm on L infinity is infinity norm of f equal to, which is defined as essential supremum of f. Okay. So we are going to prove that this is a Banach space. How will you prove this? Every Cauchy sequence converges in it. So I take a Cauchy sequence. Let Fn be a Cauchy sequence in L infinity of E. Then by definition, comma, for every epsilon greater than 0, there is a natural number n such that norm of Fn minus Fm is less than epsilon for all n and m greater than or equal to capital N. And this norm is norm on L infinity. So we have to mention that is infinity norm or essential supremum norm. So we have this. Now, which implies essential supremum norm define essential supremum of Fn minus Fm is less than epsilon for every n and m greater than or equal to n. Okay. So whenever essential supremum is less than epsilon, what is essential supremum? Essential supremum of Fn minus Fm is less than epsilon means this is nothing but actually infimum of, essential supremum is defined as infimum of m such that modulus of Fnx minus Fmx less than or equal to m almost everywhere on E is less than epsilon. This is essential supremum. Okay, for every n and m greater than or equal to n. Oh, I'm sorry, not this, these m and this m are equal. I consider this as some m dash. Okay, don't confuse with these notations. Okay. So which is less than epsilon means this will be less than epsilon. What is this? Modulus of Fnx minus Fmx will be less than epsilon. Yeah, for every n and m greater than or equal to n. So what is Fnx? Since x is a point, or what is x? X is an element in E and Fn's are defined on E. And these Fn of x, each Fn is a essentially bounded function on a measurable set E subset of R, right? And it is a real valued functions also. So Fnx and Fmx are real numbers. So Fnx minus Fmx less than epsilon for every n and m greater than or equal to n means Fnx is a real sequence which is a Cauchy sequence in R, which implies Fnx is a Cauchy sequence in real number. And we know R is Banach. Since R is Banach, the sequence Fnx converges to some f of x in R. That is, limit n tends to infinity, Fnx will be equal to f of x. Okay, and this f of x will varying with respect to corresponding x. So this can be considered as a function. That function will be clearly real valued because f belongs to R. F ആറിലാണ്, എഫ് ഓഫ് എക്സുകളൊക്കെ ആറിലാണ്, അതുകൊണ്ട് എഫ് എന്താണ് റിയൽ വാല്യൂഡായി മാറും അല്ലേ. Now we claim that our sequence of function Fn is converges to F uniformly almost everywhere on E. So how will you prove Fn converges to F? Almost, which is almost everywhere on E means when you consider a set of points at which Fn does not converges to F, that measure will be 0. Fn converges to F uniformly almost everywhere on E എന്ന് പറഞ്ഞതിൻ്റെ അർത്ഥം ഇയിൽ എല്ലായിടത്തും ഏകദേശം എല്ലായിടത്തും അത് Fn converges to F uniformly ആണ്. പക്ഷെ ചില പോയിന്റ്സിൽ യൂണിഫോംലി കൺവേർജൻസ് ഇല്ല. There are points at which Fn cannot converges to F uniformly and collection of that points whose measure will be 0. Okay, when you consider that set of those points Fn's are not converges to F, then that measure of that set will be 0. അതാണ് അതിൻ്റെ അർത്ഥം. That is the meaning of the statement almost everywhere on E. Okay, so we are going to prove that this Fn converges to F uniformly almost everywhere on E. So for that, I define two sets. Let AK equal to, define a set of all x in E such that modulus of Fk of x is greater than essential supremum of Fk. Okay, and I define Bmn equal to is a set of all x in E such that modulus of Fmx minus Fnx is greater than essential supremum of Fn minus Fm. Okay, ready. Then I define F is equal to union k equal to 1 to infinity ak union Bmn for m and n in natural numbers. Okay, ready. Then I can say that what will be measure of, this is measure, okay, measure of AK. What is measure of AK? Outer measure of AK? We know each Fk is essentially bounded, right? When functions are each Fk belongs to L infinity, each Fk is essentially bounded. Since it is essentially bounded means that will be less than or equal to its essential supremum almost everywhere on E. So if we consider set of all those points at which these Fk's are not less than or equal to, not less than or equal to means which is greater than, they are points at which Fk's are unbounded, right? ഇതിനേക്കാൾ വലുതാണ് എന്ന് പറഞ്ഞാൽ എസെൻഷ്യൽ സുപ്രീമമാണ് അതിൻ്റെ ലിമിറ്റ്. അതിനേക്കാൾ വലുതാണെന്ന് പറഞ്ഞാൽ ഏതൊക്കെയോ പോയിൻറ്റ്സുകളിൽ ദീസ് എഫ് കെ, ദർ ആർ സം പോയിൻറ്റ്സ് അറ്റ് വിച്ച് എഫ് കെസ് ആർ അൺബൗണ്ടഡ്, which can't bounded by the point essential supremum of Fk. Then you can say that clearly measure of this set will be 0 because each Fk is essentially bounded. Okay, that means modulus of Fk of x will be less than or equal to some m, capital M, bounding number m almost everywhere on E ആണ്. സോ അങ്ങനെ അല്ലാത്ത പോയിൻറ്റ്സിൻ്റെ മെഷർ എന്തായിരിക്കും? 0 ആയിരിക്കും, റൈറ്റ്? ദെൻ വാട്ട് വിൽ ബി മെഷർ ഓഫ് BMN? മെഷർ ഓഫ് BMN we know that Fnx minus F, we know each Fn belongs to capital L infinity. Therefore Fmx minus Fnx is a function, right? Since each Fn belongs to L infinity, because Fn is a sequence from L infinity, so all the elements are belongs to that space. So that Fn minus Fm is also an element in L infinity, and you know L infinity is a normed space and it is a linear space. So difference between two elements will be belongs to L infinity, right? Then you consider, then you can say that Fn minus Fm is essentially bounded. Then Fn minus Fm is essentially bounded, right? Essentially bounded. Okay, that means modulus of Fnx minus Fmx will be less than or equal to some n almost everywhere on E. What is this n? That will be essential supremum of this one, Fn minus Fm. Okay, then when you consider set of points at which this Fn minus Fm is greater than essential bound of that function, the measure of that set will be actually 0. കാരണം ഇത് ഓൾമോസ്റ്റ് എവരിവെയർ അങ്ങനെയാണ്. അപ്പോൾ അതല്ലാത്ത കേസുകളിൽ that measure will be 0. So measure of BMN will be 0. When measure of AKs are 0, then when you consider k equal to 1 to infinity AK, then union of AK's measure will be 0. Then union of BMN's measure will be 0. So hold the union. That means measure of F will be 0. Therefore measure of F will be 0. അല്ലേ, രണ്ട് സെറ്റുകളുടെ മെഷർ 0 ആണെങ്കിൽ ദർ യൂണിയൻ്റെ മെഷറും എന്ത് തന്നെയായിരിക്കും, 0 ആയിരിക്കും. അല്ലേ, ദാറ്റ് ആർ ദ പ്രോപ്പർട്ടീസ് ഓഫ് ഓക്ടൽ മെഷർ, ലെബർഗ് മെഷർ. So you get measure of F is equal to 0. Okay. So what is measure of F? Union of these two sets. Now we are going to prove that actually then we prove our sequence Fn converges to F in F complement, and this F belongs to L infinity of E. We defined we have taken the Cauchy sequence Fn. Okay, now we have a function F, right, because Fn converges to F uniformly almost everywhere on E. This is we need to prove, and this F is defined by limit n tends to infinity Fn x equal to f of x, point-wise convergence. Okay, then I will prove Fn converges to F in the F complement. That means Fn converges to F almost everywhere. Okay. Ready. Now consider to prove this we have to consider limit n tends to infinity norm of Fn minus F with respect to the maximum SIP norm, essential supremum norm, Fn minus F infinity. We have to prove that this is equal to 0. Okay, so what will be this? Limit n tends to infinity. Okay, essential supremum, by definition it is essential supremum of Fn minus F, essential supremum of Fn minus F. Okay, that is equal to limit n tends to infinity. What is essential supremum of Fn minus F? That is nothing but infimum of modulus of Fn x minus infimum of set of all essential bounds. Suppose m p such that infimum of such p such that Fn x minus f of x modulus of Fn x minus f of x less than or equal to p almost everywhere on E. Can you see it? Yeah, infimum of p such that Fn x minus fx less than or equal to p almost everyone E. അതായത് Fn x മൈനസ് എഫ് ഓഫ് എക്സിൻ്റെ അപ്പർ ബൗണ്ട് ആയിട്ടുള്ള പി കൺസിഡർ ചെയ്യുന്നു ഓൾമോസ്റ്റ് എവരി വൺ ഓൺ ഈ കേസിൽ. ആ പികളിൽ ഏറ്റവും ഇൻഫിമം ആയിട്ടുള്ള നമ്പറിനെയാണ് നമ്മൾ എസെൻഷ്യൽ സുപ്രീമം എന്ന് വിളിക്കുക. സോ ദിസ് വിൽ ബി, സോ വാട്ട് ഈസ് ദിസ്? ലിമിറ്റ് ഇൻ n tends to infinity infimum of set of all p such that what will be Fn x minus Fn x minus f of x. You know, if x is fixed, when x is fixed, modulus of Fn x minus f of x will be tends to 0 because Fn x converges to fx in real numbers as real numbers, right? So this will be nothing but 0. So this goes to 0, right? Therefore set of all infimum of p such that Fn x minus f of x less than or equal to p means this whole thing will goes to 0. So infimum of 0, right? Infimum of 0. So infimum of 0, which means which always implies 0. So you get limit n tends to infinity subnorm of or infinity norm of Fn minus f is equal to 0. So which means Fn converges to f uniformly almost everywhere on E. Okay, then we need only prove that this f is also belongs to our capital L infinity. So next we need only prove this f belongs to L infinity of E. For that we want this f is essentially bounded. Okay, so what will be the essential bound of this f? Is it essentially bounded? Since the convergence is uniform, each Fn is essentially bounded, F will be also essentially bounded, right? Yeah. Since the convergence is uniform and each Fn is essentially bounded, F is also essentially bounded. So, F is a real valued function which is essentially bounded and defined on a measurable set E. Therefore, F belongs to L infinity of E. Therefore, L infinity is a Banach space. Therefore, L infinity is Banach.